So now that we've seen the unit circle and we've come up with the trig functions for different angles along the unit circle, we're going to change gears slightly and just sort of stretch the unit circle out into the coordinate plane. So rather than, let's just start off with, let me show you a sort of example here. Rather than being confined to just a circle with radius 1, let's just say I have some angle theta. Its initial side is the x-axis, its terminal side is somewhere in space. And let's just pick some point on here. It could be any values I want. So let's just say it's x and y. So this is some x value and this is some y value. And we're going to basically ask the question, well, what is sine of theta in this situation? Now notice we don't actually know what this distance is, or radius if we're thinking about the circle. It's not just stuck at 1 anymore, even though the unit circle is a great way to evaluate different angles. We want to stretch this out to be any distance we would like. So we're going to slightly adjust our formula that we got in the previous lesson in section 4.2. So now what we're going to say is sine of theta is actually going to be this opposite side of the triangle, y, over whatever that distance is. Now instead of d, usually we use r to sort of make us think about circles. So we're going to say that sine of theta is now just y over r, whatever r might be. With the unit circle, it was 1, and so we had r equals 1, and then sine of theta was just y. Now we're changing things up just a little bit. Cosine will be x over r. Tangent of theta actually doesn't change. It's y over x. And then we have the reciprocal functions as well. And we just take the reciprocal of each of those. And then cotangent of theta equals x over y. And that's really all that changes. So this video we won't be doing too much because most of what we talked about that applies in this video also worked out in section 4.2. But we will see a couple more examples for this content. And our goal today is to be able to find the trig function for any angle, not just if we're confined to the unit circle or a right triangle. Okay. So what I want to do to start off with is find the value of all 6 trig ratios for some angle. Trig ratios or functions, right? So this is sine, cosine, etc. For some angle theta. Given that the point -1, 2 is on the terminal side of theta. All right, so the first thing to do is to draw a quick sketch. So let's go ahead and draw our coordinate plane. I have x and I have y. The point -1, 2 is roughly here. And so that means if I draw a line going through the point -1, 2, the angle I'm talking about is this angle here, theta. So starting at the x-axis in standard position and then ending on that ray that goes through -1, 2. So right off the bat, we can actually write down what our x and y values are. So we have x, the point xy is the point -1, 2. But I don't know r yet, although it's not too tricky to find. All you have to really do is the Pythagorean theorem, because notice that we sort of have a triangle here, length 1, length 2, and r is just the hypotenuse. So let's go ahead and determine a value for r. Now when you're doing negatives, please make sure to put the parentheses around the negative before you square it. If you don't, you'll end up with -1 squared equals -1, which is technically not incorrect because this is negative of 1 squared if you're following PEMDAS. So what you want to make sure to do is parentheses -1 squared, which is -1 times -1, which should give you a +1. So this is not true, and this actually is true. So that's my little aside there. Okay, so anyways, back to our original question, which was what is r? What is that distance from the origin to this point? And so if you go ahead and do 1 squared plus 2 squared, you should end up with 5, and so r is just the square root of 5. So at this point, I have all the details I need. I have x equals -1, y equals 2, r equals the square root of 5, and I can go ahead and actually solve for all of the trig ratios. So let's go ahead and just kind of make a box here. Sine of theta is y over r, so 2 over the square root of 5. Now, this is okay for me. I don't mind if you leave radicals in the denominator, but on Delta Math and many other sources, for example, ACT, that kind of stuff, they will ask you to rationalize the denominator. So you should really write this as 2 times the square root of 5 over 5. I obtain that, once again, I'll do this as a reminder, I'm multiplying the top and the bottom by the square root of 5. Okay, so that was sine. For cosine, we're going to get -1 over the square root of 5, which is just -√5 over 5. And then for tangent, I need y over x, so 2 over -1, which just gives me -2. Now I'm going to flip them for their reciprocals. So for cosecant of theta, I end up with the square root of 5 over 2, which is just r over x, or sorry, r over y. For cosecant, or sorry, for cosine, I'm going to take secant, which will just give me the negative square root of 5. And then for cotangent, I end up with x over y, so I end up with -1/2. So notice I'm really just going back to these definitions I gave you here. And I'm just, for example, cosecant, I just did r over y. For secant, I did x over y, and I'm getting those numbers here. And then those are my answers. So we end up with sine, cosine, tangent, cosecant, secant, and cotangent of theta. Okay, so this is a problem where I gave you the point that's on the terminal side. Let's take a look at another type of example where you have to work a little bit harder to find the actual point that's on the terminal side. So I'm going to tell you in this problem, find all 6 trig ratios of theta, given that, so notice this will be a little bit different. Sine of theta is going to equal -5 over 7. And I'm also going to tell you that secant of theta is less than 0. Okay, so the first thing to do is just really figure out what the heck do we have here. So for sine, I actually have the y value and the r value of my coordinate. I don't know x yet, but I know that y is -5. R can never be a negative number because it's a distance, right? It's a distance or a radius. You can't have a negative radius. So that's why I know that the negative is with the 5. And actually, just to make the notes sort of cleaned up here, let's do that. So r is 7. Okay, so I will have to figure out x, but before we do that, so that's all from this, let's figure out what this is telling me. So remember, we talked in a previous video about which quadrant the functions are positive in, and we said all of them are positive here. We said in the second quadrant, we had sine and cosecant were positive. Well, that doesn't make any, we can't be in quadrant 2 because notice how in this example, sine of theta is actually negative. we said in this quadrant down here, the only functions that were positive were tangent and cotangent. And so that tells me that in quadrant 3, I know that sine of theta will be negative, cosecant of theta will be negative, cosine of theta will be negative, because x is negative over here, and y is negative down here, and then also secant of theta will be negative. So this information actually tells me that I'm now going to be in quadrant 3. Well, I guess this information combined with this information tells me that I'm in quadrant 3. So really what that tells me is that x has to be a negative number. Okay, now let's go ahead and draw our sketch, just like we did in the previous problem. I don't know exactly where theta is, but I know that it's in quadrant 3. I know that it goes through the point x negative 5, and I also know that this distance here is 7. So if I draw a right triangle with the x-axis, then I know that this hypotenuse is 7, the y value is 5, so I'll just stick with 5 for now, although you could make it negative if you want. And I don't know what x is. So let's go ahead and set up our Pythagorean theorem. X squared plus negative 5 squared has to equal 7 squared. So that means that x squared plus 25 equals 49. Which tells me that x squared equals 49 minus 25. You can go ahead and get a calculator out, and you should end up with 24, which tells me that x equals plus or minus the square root of 24. Now, based on our work up here, since we're in quadrant 3, we know that x does actually have to be a negative number. So that means I'm going to pick the negative and say that x equals negative square root of 24. Now, once again, the square root of 24 is fine for me, but it's not actually simplest radical form because you could rewrite 24 as 4 times 6. 6 does not have a perfect square, but 4 does, and so we end up with negative square root of 4, which is 2, times the square root of 6. So this is what I will be using in this problem. It's not the actual answer yet, but that is what I'm going to be using. So let's go back up here. We now know that x is negative 2 times square root of 6. And so we could actually solve the problem at this point. I know what sine of theta is that was given in the problem. I can now get cosine of theta. Cosine of theta will be negative 2 radical 6 over 7. Tangent is y over x, so that's going to be negative 5 over negative 2 root 6. Rationalizing the denominator, I end up with negative, well, let's go ahead and we don't need the negatives anymore since it's a negative over a negative. 5 radical 6 over 2 times a regular 6, so I end up with 5 over 12 with a root 6 on there, so that was tangent, cosine, and sine. Let's go ahead and do the reciprocals now. So I have cosecant of theta. I just have to flip the sign for this one. For secant of theta, I'm flipping cosine. But once again, I need to rationalize the denominator, so I'm going to have, this is my answer for secant. And then for cotangent, this is x over y, so I can just go back to what x was and put that over y. Since they're both negative, I'll just go ahead and get rid of those negatives. And that's the answer. We are now totally done with this problem. You have seen 2 different types of problems. In the first one, you were given the point, and you had to actually figure out what to do there. That one's usually a little bit more straightforward because you don't have to figure out which quadrant we're in. You can just kind of get R and then immediately solve it. In the second problem, you were given a trig function, and then you kind of had to figure out which quadrant we were in, solve for the missing piece, either x, y, or r, and then from there you could get all of the rest of the trig functions. Okay, before we end section 4.4, that actually was the last example I want to do. I want to talk briefly about the word reference angle. I brought this up previously, but it does come up quite a bit in textbooks and also on Delta Math. I don't really think reference angles are super useful. They were used a lot more historically than we do now, but it still comes up often enough that you should know what a reference angle is. So basically, if you have some angle theta, and if you check back into a previous video, you'll see almost this exact same diagram. If you have an angle theta and I make this right triangle with the x-axis, notice I'm not making a right triangle with the y-axis over here. It always is a right triangle with the x-axis. Then this angle in here, so the angle that's made with the x-axis, which I called phi in a previous video, this angle phi is the reference angle. And usually we use the notation theta with a little tick mark next to it, and we say sometimes this is theta prime, or you might just say theta dash or something, but this is the notation for the reference angle. Another example would be if I had my theta all the way over here. Once again, I would make a right triangle with the x-axis, and my reference angle is right there. So just something to note, definition-wise, when we're talking about that reference angle, we're talking about the angle that is made with the x-axis, and it always has to be an acute angle. So you're basically making this right triangle with the x-axis, and then what is that angle? And depending on which quadrant you're in, for example, this problem I just wrote, to find theta prime, you would first note that these two angles should add up to 360 degrees. So therefore the reference angle was just 360 minus theta. So you'll also see this sort of notation show up. In this example, you'll notice that they are supplementary. So that means that the reference angle would just be 180 minus theta. The last quadrant that you might have an angle in where you would have to do this, notice if you had an angle of theta in quadrant 1, you don't actually have to do any work. Your angle is your reference angle. But let's say I was in quadrant 2. So if I made a right triangle here, what I would want to do to get the reference angle, which is kind of this little bit, notice that 180 degrees plus my reference angle equals the original theta. So that means that my reference angle would be theta minus 180. Once again, I'm just putting these formulas down for your own reference. These will come up if you start looking trig up on Google or in other textbooks or Khan Academy or even in Delta Math. They will mention the reference angle. You can do all of trig without a reference angle if it makes intuitive sense to you. You don't have to worry about it. But it's really up to you just for your notes, so you have this somewhere in there. But other than that, we are done with